Hello, this is the Mr. Dow Maths channel. Today I'm going to be going over the third part within our Further Vectors series, which is going to be the interactions between the different types of graphical objects, I'd assume, or I'd say, within 3D space that you're going to be working with in the WJEC. Of these graphical objects, the two that are relevant to you are lines and planes. Obviously you can also define points, but they're a little trivial because there isn't much different from defining a point in 3D space than there is in 2D space. First of all, it's a pretty basic question, but oftentimes with the tools that you are provided at GCSE and even A-level mathematics, the question can actually be quite a little bit tedious if you consider it within a very, from a very basic viewpoint. The question is, if I have a line in, I guess, maybe even n-dimensional space, but for now I'm going to consider just two-dimensional space over here, and I have a point somewhere in this two-dimensional space, then what's the shortest distance between this point over here and this line? And let's call this point P. And this is a very interesting question because if I consider the shortest distance between a point and a line, then very clearly, okay, I can't really take any detours outside of what my shortest path will be. So clearly there's a shorter path than this. There's going to be a shorter path than this. Very obviously, not to insult your intelligence over here, the perpendicular between the line and the point will be the shortest distance. The only problem here is that oftentimes what you are taught at the A-level further maths spec is that first of all you'll need to work with the perpendicular to the line, and then you'll have to consider where it crosses the point here and then where it crosses the line that you originally worked with. And that in itself, that is a lot of algebra that you have to do, a lot of arithmetic, and ultimately it's just a little bit cumbersome, and we just like a lot of other different ways in which we can approach a problem. It's always nice to have some other approach that you can use, some other view that you can have on a problem. So we're going to work with 2D first of all to kind of establish a strong understanding, and then we can move up to 3D because the kind of numerical way of representing things doesn't change much, but the structure obviously does because we're quite literally moving up a dimension. So we're going to talk about that because I feel like kind of, discussing that is a lot more interesting than just, giving the formulas and then, working through answers over here. Ultimately, what my goal is to teach you 3D vectors in a way that's more intuitive so that you actually have an understanding of the subject instead of just applying formulas where you, I guess, deem fit. Okay, so the interesting bit is that there is a point distance formula between a point and a line. And the nice thing is that we can define our line as ax plus by plus c equals 0. Crucially, I have to define my line like this because the issue is if I use y equals mx plus c, then I have two cases where I can't actually represent my line in that sort of way. Namely, when y equals some constant value or x equals some constant value, because for those values m isn't defined. Or rather m is 0. If you're going to say m is 0 over here, then you can say y equals a does work in a sense where a equals c, but x equals a can definitely not, it can't work at all because a vertical line, does it really have a gradient? No. It doesn't change over a certain value of y. So yeah, To remain consistent with our sort of works, we're going to use ax plus by equals c, which is basically just the overarching framework that is much more useful than just y equals mx plus c due to the reasons that we just discussed. And let's say our point over here is just x, y. The point distance formula, which gives us the distance between these points, is the modulus of, if I were to define these points, it's going to be ax1 plus by1 plus c divided by the square root of a squared plus b squared. And this is your point distance formula for between a line and a point. But there's a more general way in which you can, talk about this, and that is by considering vectors. So this is one nice way to represent a line, okay? And I highly encourage you, with the information that you have here, that you try and derive this point distance formula, because it's not out of your reach at all. Obviously, the astute among you, further mathematicians, A-star students, it shouldn't take you that long to figure this out. And it is good exercise as well, just to get a good grasp of how the mathematics behind these sorts of formulas work. So yeah, let's bump it up a notch. Essentially, I think I'm going to go with three-dimensional vectors, or three-dimensional lines and three-dimensional points, just to kind of illustrate my point as to how the general sort of system works. So let's say I've got my line L1 and I'm going to describe it as the position which equals my starting vector plus some lambda times my direction vector, which I'm going to call B. And then P will just be x1, y1, z1. Z1 because now we have three dimensions. Crucially, what we have to define now, which we didn't define earlier but we should have, is the origin. Obviously then before, because I gave you the general formula, and okay, yeah, I forgot to say this, but the formula that I wrote on the board is present in your formula booklet, so although there's no need to memorize it then, I think you still should be very familiar with it. So much so to the point that you don't even need to look into your formula booklet to use it. Anyway, that was a bit of an aside, but if we define the origin, then we can define the origin vectors. As you know from the previous video, defining the origin and then using the origin vectors is in fact a very useful tool, because now we have a separate way to define a lot of things within our sort of diagram over here. So if we have P, and I'm going to define the point where the perpendicular to my line L1, which passes through P, meets the line L1. Bit of a mouthful to say there, but I think you know what I mean. That point Q over there will represent what the intersection is. And if we take the mod of PQ, which is going to be or if you like, the length of PQ, then we just get our perpendicular distance, i.e. the shortest distance between P and Q. Now, I think it's a good exercise now to pause and kind of grapple with this problem as to how we can, work out the perpendicular distance. But I will go through this now. The idea is that just as A and B are vectors, we can expand them outwards and we can add, multiply and subtract them however we normally do with vectors. So we have the position R equals A plus lambda B. So maybe A is some arbitrary point over here and B is some arbitrary point over here. And then defining the origin points, obviously, or origin vectors, obviously. Then you have little a, little b. Or rather, sorry, because this is the direction vector, I should be a little bit careful over here. The direction vector will be b minus a. If you haven't already, before going into this video, obviously watch the video before this part 2, which is going to explain a lot of things that I'm doing over here. Okay, well, just from observation, what you can figure out actually is that Q is just some position on the line L1. Therefore, you can actually just replace this Q with maybe our general position R. So the origin vector to my R, my position now, just becomes little r, and I can use this line to kind of work with and ultimately try and get my answer. But the nice thing now is that we know how to find PR, because now we have a position vector P and a position vector R. Expanding this out, what you get is the x component of A, the y component of A, and the z component of A. And obviously, because this is a constant lambda, what this really is doing is that it's multiplying the I, j, and k components, again something that was covered in the last video, by some constant lambda. So, in essence, what's happening over here is just this. Lambda times, again, the x component of the direction vector, the y component of the direction vector, and the z component of the direction vector. And this is your position vector still. This idea and this idea over here are the same. Obviously does look a little bit scary at first. I hope it isn't as scary by the end of the video, but the essential idea over here that I've done is I've split the vectors over here, which are just in their normal form, like let's say A is this vector here, into their x, y, and z components, which you will see later on why it's so useful we do that. Now consider PR. Just erase this. Consider PR. We know what the position vector for P is, clearly because it's x1, y1, z1, or rather I'll just use x, y, and z. It's a little bit easier. But yeah, it's x, y, and z. I've put this in sort of column vector form because if we go from the origin, that is what the point that we land on is if we take whatever the values of x, y, and z are. Crucially, it doesn't really matter what P is. It does work every single time, no matter what real value of x, y, and z you choose. Any 3D vector with a real entry for x, y, and z, this will work. So, PR is this vector right here, but crucially it's also this, which means that what you're doing is, or what another way to think about the, I guess the walk from P to R is going against the flow of P and with the flow of R, so minus P plus R minus P. And the nice thing about this is that, well, again, it's a very general rule. It will work for any sort of system that you'll apply to. Obviously, as long as you apply it to a system that is actually useful and not trivial. But you don't need to worry about that at all. Here we have R minus P. But crucially, we know what R is and we know what P is as origin vectors. Therefore, we can just substitute. We have ax plus lambda dx, ay plus lambda dy, az plus lambda dz, and don't forget to underline. It's very important that you use correct notation as well. And then you subtract your point P, which is going to just be a general point, x, y, z, which will be ax plus lambda dx minus x, ay plus lambda dy minus y, az plus lambda dz minus c. So, a little bit intimidating over here, but all this is really saying is, what's the component of P, what's the component of R? If I subtract them together, what will I get? And that's just the component of PR. If you give these like labels, this is the component of P and R, which is X, this is Y, and this is Z. I use big letters over here just to, I guess distinguish between just the point P and PR. After this, it's just Pythagoras, because what you're trying to find is the distance between this point and the line, which is just going to be the closest distance, which we defined to be R. Considering that, what you're really just doing here is just Pythagoras. Consider x squared, which is just going to be this expression squared, plus y squared, again, the second component, this squared, plus z, without the bar in the middle, z squared. And that is a sort of general way in which you can work out the distance between a point and a line. Crucially, this method works in 2D as well. Okay, so this method in itself, it's pretty useful that you learn this method. Not a very hard method to learn, it just requires you to be a little bit geometrically apt at things, very basically it's just something that's a little bit tedious and requires you to understand the mathematics behind why we're sort of doing these calculations a little bit more than anything else in further mathematics. If anything, this is a lot more intuitive than it is, I don't want to say rigorous, it's a lot more intuitive than it is hard work. I'll say that. But I want to go back to our point distance formula. So what I wrote on the board was this. D equals, and D being the shortest distance between a point and a line, being ax1 plus by1 plus c divided by square root a squared plus b squared. Now there's another formula which looks extremely similar, which is this, and I'll call this D2 and D3. So a bit of a clue there. And what I should be saying is this is for, let's say, P, which is x1, y1. So I have another formula that is perfectly valid. But it serves a sort of different purpose. Obviously it's still calculating the shortest distance between a point and something, but what is that something that you're working with? And the clue lies in the numerator. From the previous video, what you should immediately spot over here is that, wait, ax, by, cz, d. This is the Cartesian form for the equation of a plane. Therefore, this form actually just tells you the distance between, or the shortest distance between a point and a plane. Pretty simple, and honestly, it's, I think, quite like elegant that just adding another component gives you something that looks very similar numerically, but at least graphically it looks a lot more different. Okay, so this is another useful formula that you can learn. This is just a sort of formula that you can just have in the back of your head. This one, it's a lot more useful within the TMUA and exams of that sort. But obviously that's within your choice to pick. This is really just a sort of a side that you can use. Not something that you are obliged to use in the exam. Now there's other interesting interactions that you can have, like between two lines. Between two lines in 3D, or rather let's talk about 2D first. The possibilities for 2D different ways that a line can interact in 2D, they're very simple. Either they intersect or they don't. So two lines can intersect at some point, maybe like x, y. Or they don't intersect at all. In other words, they're parallel. So 2D, pretty simple to understand. 3D, it becomes a little bit more complicated. Clearly, you can have lines that intersect in 3D. There's nothing stopping you from intersecting two lines in 3D. So, kind of illustrating this, I can have two lines like this, and they can still intersect, obviously. They can also be parallel, if you like. So I can have another line, which is maybe something like this. And these two lines, sure, parallel, great stuff. But there's another kind of interaction between lines that you can encounter, which is skew lines. They aren't parallel, ultimately because their direction vectors, they are not the same. But the way they are, they're not exactly parallel, or they aren't parallel at all, they just never meet. So it's kind of hard to sort of, put on a 2D board. I guess if I were to kind of show this, it would be like these two markers, imagine these two are lines, then these two lines are really, really close to each other at one point. But as you diverge off to some huge parameter, maybe lambda equals 1,000 for that line, then clearly it's never going to meet these two lines. Again, if you have these two lines over here, so these markers are lines, right? Clearly they can get very, very close to each other, really, really close. But there's a possibility that they're never going to meet. Or rather, they can never meet if I'm going to arrange them like this, because they get really close. But the thing is, really close doesn't mean that they touch or they intersect at all. So that's a very interesting case within 3D. Two lines can neither be parallel nor can they intersect. Therefore, they are skew lines. I guess if I had to represent it in 2D, I'd have maybe an offset like this, and then I choose a point here, and then I draw the perpendicular like this. Draw perpendicular here, and a perpendicular like this. So yeah, this is one way in which you can talk about, or rather represent, a skew line. So this is the shortest perpendicular distance between the skew line, the perpendicular that I've just drawn. So yeah, that is about it really. Oh yeah, one more thing. There's interactions between a line and a plane and two planes. In the next video, I'll go over calculations and how you can work with these. Ultimately, it's a lot more geometric interpretation than the calculations that you are familiar with, which is why this topic is oftentimes either only hated or liked. There's no in between with this sort of topic. Ultimately, because it's just so different from anything else that you learn in AS Pure. But there's another interaction which you can, or which you should worry about, which is a plane of this sort extends infinitely in all directions with the origin here and maybe some line that passes through like this. So it crosses through the plane here, goes behind it, emerges out and continues on. If I define a normal like this, then I have this sort of intersection point over here. What you're typically asked to do is you're asked to find maybe what the smallest or the acute angle between the line and the plane is. And ultimately it is just a matter of kind of working with the direction vectors of both the, or rather the direction vector of the line and the normal vector of the plane. So that's one very interesting system that I hope you consider before the next video comes out. Obviously with any video that I put out, I hope that you also kind of explore these topics beforehand. Ultimately it makes you a lot more ready to tackle the problems later on. And I'd imagine it makes your teacher's job a lot more easy as well. Finally, the last interaction that you want to consider is between two planes. Between two planes, if we have a sort of side view on them, so they look like lines to us, we can clearly see that the normal vectors are like this. Horrible normal vector that. Alright, so the normal vectors are like this. There's going to be a line over here of intersection, which, as far as I am aware in the WJEC, you do not need to calculate. I'm pretty sure in other exam boards like EdXL or Cambridge IGCSE, you are required to do that. So I suggest you check that out. But in the WJEC, you are not required to. What you are required to do is calculate the angle between these planes, which I also suggest you do. So I'll leave that as an exercise. These two vectors are key. I'll give you this hint. So if you have a normal here and a normal here, then these two normals, I guess, if you were to kind of extend them outwards, because just remember what you know about vectors, you can move them around, do whatever you like with them, as long as they have the same components, they are the same vectors, no matter where they are in the space that you put them. So kind of consider this sort of structure. So yeah, this is the structure that you want. And I think I'll leave this as a sort of exercise for you to kind of play around with, have, or grapple with a little bit. But yeah, these are all the sort of interactions that you want to work with. I've gone through one of them, and the rest I hope you can figure out later on. In a later video, maybe next week, I'll go over the calculations that you are required to do with these sorts of interactions, and a special question which involves you calculating the equation of a plane if you're given 3 points. So that in itself a very interesting question. But next week the agenda is go through how you do calculations with this setup, this setup right here, which is two planes, and the interaction between a line and a plane, and skew lines. So yeah. Thank you for watching as always.